an introduction to swarm algorithms for functional and business use cases. First of all, welcome back to this second lecture. In this lecture, we'll lay the groundwork for understanding swarm intelligence by exploring its biological inspirations and fundamental principles. What is swarm intelligence? Swarm intelligence refers to the collective behavior of decentralized, self-organized systems, typically inspired by natural phenomena. It's a subfield of artificial intelligence that studies how simple agents can work together to solve complex problems without centralized control. The emergent behavior resulting from the local interactions among agents often leads to efficient, adaptable, and robust solutions. Biological inspirations. Swarm intelligence draws inspiration from various natural systems where individual agents, such as animals or insects, exhibit collective behavior. Some key examples include ant colonies. Ants communicate through pheromones, which are chemical trails that influence the behavior of other ants. This simple form of communication allows ants to find the shortest paths to food sources and adapt to changes in their environment. Bird flocking. Birds flying in flocks adjust their positions based on the movements of their neighbors. This behavior helps the bird and the flock avoid predators, conserve energy, and navigate efficiently. Fish schooling. Fish in schools exhibit synchronized swimming patterns to evade predators and to optimize foraging. The local interactions among fish lead to the formation of cohesive dynamic groups. Bee foraging. Bees use a waggle dance to communicate the location of food sources to other members of the hive. This collective decision-making process ensures efficient resource allocation. Key principles of swarm intelligence. Swarm intelligence systems are characterized by several key principles. 1. Decentralization. There is no central control governing the behavior of individual agents. Each agent operates based on local information and simple rules based off of what it is. And so if it's a ant colony, it will function based off of its ant algorithms. If it's a particle swarm algorithm, it'll function off of particle swarm, etc. Self-organization. Agents interact with each other and their environment to produce coherent global behavior. This emergent behavior arises from the bottom up rather than the top down, meaning that you're not programming in the behavior, you're just giving the characteristics, and then the behavior is emergent as a result of the characteristics. Key principles of swarm intelligence. Adaptability. Swarm systems can adapt to changes in the environment or system conditions. The flexible nature of these systems allows for robust performance in dynamic settings. Scalability. Swarm intelligence systems can scale effectively with the number of agents. The same principle applies whether the swarm consists of a few agents or millions of agents. Robustness. The decentralized and distributed nature of swarm systems makes them fault tolerant. The system can continue functioning even if some agents fail or are removed. That's the whole point of the system, is that rather than just throwing like one bot at a problem, you throw 1,000 bots at the problem, and then if 900 of the bots fail, 100 bots still get through. Even if 999 of the bots fail, one of the bots still gets through. Swarm intelligence algorithms. Several algorithms have been developed based on the principle of swarm intelligence. Here are some of the most well-known ones. 1. Particle swarm optimization. Particle swarm optimization is inspired by bird flocking and fish schooling. PSO optimizes a problem by iteratively improving candidate solutions based on the movement and behavior of particles, agents, in this search space. And I highlight this alone because we're going to dive deeper, especially when it comes to business and real-world practical applications, a lot deeper into particle swarm optimization, what it is, how it works. I'm highlighting that up front, that we're going to dive a lot deeper into PSO very specifically. Then next we have ant colony optimization, or ACO, based on the foraging behavior of ants. ACO is used for solving combinatorial optimization problems. It employs artificial ants that deposit pheromones to build optimal solutions. Bee algorithm, modeled after the foraging behavior of honeybees. This algorithm uses scout bees to explore new solutions and worker bees to exploit known good solutions. The firefly algorithm, inspired by the flashing behavior of fireflies. This algorithm is used for optimization problems. Fireflies are attracted to each other based on their brightness, which is related to the quality of the solutions that they represent. In conclusion, in this lecture, we've explored the foundations of swarm intelligence, including its biological inspirations and key principles. Understanding these basics is crucial for appreciating how swarm algorithms work and their potential applications. In the next lecture, we'll delve deeper into specific swarm algorithms, starting with particle swarm optimization, or PSO. We'll explore how PSO works, its underlying mechanics, and practical examples of its use. Thank you for your attention, and I look forward to seeing you in the next lecture.